Dear students, so far we have seen the efficiency of Carnot's cycle using Q1 and Q2 heats at source and sink, and also we have seen the efficiency of Carnot's engine using the temperature of the sink and the temperature of the source. Today we are discussing the concept of reversibility of Carnot's engine. Now let us try to understand why the Carnot's engine is reversible. What are the reasons for the Carnot's engine to be reversible? Why Carnot cycle is reversible? We can quote here around four reasons. The first reason is the total absence of friction between the piston and the cylinder. So whenever we discuss about the piston in the cylinder, we have added a word called frictionless. So friction is totally absent between the piston and the cylinder. The second reason is the extreme slowness of the operation performed on the working substance. And the third reason is the strict constancy of temperature under which isothermal changes are performed by using perfectly conducting base for the cylinder. So the base of the cylinder is perfectly conducting, it is assumed, and also the temperature of the process, isothermal process, it is maintained constant. And the fourth important reason is the total prevention of the loss of heat from the gas by using a perfectly heat insulating material for the wall of the cylinder. So whenever we use perfectly conducting material, it is assumed as it is perfectly conducting. And also whenever we use for the walls of the cylinder, the insulating material, it is assumed or it is designed, it is assumed as it is the material is perfectly insulating. Of course, we are discussing about the ideal engine. Hence, Carnot's engine can be operated in the reverse direction, and Carnot's cycle can be reversed for its operation. So we have seen the figure in the PV diagram, the PV diagram which shows a perfect uh, Carnot's cycle. Now here we see that that Carnot cycle can be reversed in its operation. Instead of absorbing Q1 amount of heat from the source at temperature T1, transferring a part of heat into the sink at temperature T2, and converting Q1 minus Q2 amount of heat into work, one can operate it in the opposite direction. Now, in this opposite direction or in the reverse cycle, the engine absorbs Q2 amount of heat from the sink at temperature T2. By doing external work W on the working substance, an amount of heat Q1 is released to the hot body at temperature T1. So this reverse operation of the Carnot cycle and the flow diagram of the reversible engine is shown in the figure. In Carnot's cycle, you have seen the A, B, B, C, C, D, and dA. It was isothermal in Carnot's cycle. It was from A to B, it was isothermal expansion. From B to C, it was adiabatic expansion. From C to D, it was isothermal compression. And from D to A, it was adiabatic compression. Now, in the reverse cycle, you can see the arrow runs from A to D, D to C, and C to B, and B to A. So isothermal A to B, B to A is isothermal compression, C to B is adiabatic compression, and C to D to C is isothermal expansion, and then A to D, it is adiabatic expansion. So the process is reversed, and this reverse operation of the Carnot cycle is given by this PV diagram. Now the flow diagram, which is already in description, we have already described the reverse process, and its flow diagram is given here. You can check here. An amount of heat Q2 is absorbed at T2 temperature, and an external work W is done on the working substance, and an amount of heat Q1 is released to the hot body at T1 Kelvin, and this Q1 is nothing but Q2, which is the heat which is absorbed at the sink, plus external work done on the working substance. Now this reverse process we can describe as far as the working substance, source, sink, and insulating stand is concerned, as we explained in uh, Carnot's engine operation. Here in the reverse case, what we do is the working substance is allowed to expand adiabatically from A to D by placing the cylinder on the insulating stand. Then it is allowed to expand isothermally from D to C by placing the cylinder on a sink, where an amount of heat Q2 is absorbed from the sink. Then the gas is compressed adiabatically from C to B by keeping the cylinder on the insulating stand until the state B is reached. Finally, the gas is compressed isothermally by placing the cylinder on the source till the state A is reached. This is the principle of a refrigerator. So this brings to us the difference or the working style of Carnot's engine and refrigerator. In the forward direction, it is Carnot's cycle or Carnot's engine. If the Carnot cycle is reversed, then it is the principle of a refrigerator. We see here Carnot cycle is we know that Carnot cycle is perfectly reversible. We have given the reason for it. So it can work as a heat engine or as a refrigerator. In the forward direction, as we have already seen, it is heat engine, Carnot's heat engine, and in the reverse direction, it is the refrigerator. Now, when it is operated as a heat engine, it absorbs heat Q1 from the source at a temperature T1, does an amount of work W, and rejects heat Q2 to the sink at temperature T2. Of course, T2 is less than T1, and this is shown in the figure A. So first figure that you see here, it is shown in the figure A, which we have already seen earlier. When it is operated as a refrigerator, it absorbs heat Q2 from the sink at temperature T2. W is an amount of work done on the working substance by some external means, and it rejects heat Q1 to the source at temperature T1. Of course, T1 is greater than T2 as shown in the figure B. In the reverse Carnot's operation cycle, heat flows from a body at a lower temperature T2 to a body at higher temperature T1 with the help of external work done on the working substance. This action is found in the refrigerator. In every cycle, in the every reverse operation, in every cycle, heat Q2 is extracted from the cold body. This will not be possible if the cycle is not completely reversible. Now let us see the coefficient of performance. Now we have seen the efficiency of heat engine. Now when you consider the refrigerator, the efficiency of the refrigerator is measured by a quantity called coefficient of performance. Now, what is coefficient of performance? How it is calculated? Now, if Q2 is the heat absorbed at the temperature T2 and Q1 is the heat given to the hot body at temperature T1, then the work done on the machine is Q1 minus Q2. So thus, coefficient of performance of the refrigerator can be defined as the ratio between heat absorbed and work done on the engine. So coefficient of performance Cp is nothing but heat absorbed divided by work done on the engine. And heat absorbed, we know it is Q2, and the work done on the engine is Q1 minus Q2. So Q2 by Q1 minus Q2 gives the coefficient of performance for a refrigerator. Now, for an ideal gas, we know Q1 by Q2 is T1 by T2. Now, this Q1 by Q2 is equal to T1 by T2 can be written as Q1 by Q2 minus 1 is equal to T1 by T2 minus 1. So that can be simplified as Q1, that can be written as Q1 minus Q2 by Q2 is equal to T1 minus T2 by T2. So that can be written as Q2 by Q1 minus Q2 is equal to T2 by T1 minus T2. So coefficient of performance is written, the expression for coefficient of performance is written in terms of heat temperatures of source and sink. Now we have seen coefficient of performance is equal to T2 by T1 minus T2. Now we will give an example with some numerical values. Suppose 200 joules of energy is absorbed at lower temperature and 100 joules of work is done on it by external help. Then 200 plus 100, that is 300 joules, are rejected at the higher temperature. The coefficient of performance is Cp is equal to Q2 by W, and that is nothing but Q2 by Q1 minus Q2. Now this Q2 is 200 joules of energy that is absorbed divided by 300 minus 200. 300 is the heat rejected at the higher temperature, and Q2 is the energy that is absorbed 200, that comes out to be 2. So here one of the interesting thing that we see here is coefficient of performance of refrigerator here is 200%. Now we have seen in the case of heat engine, efficiency could not be more than 100% because of the practical problems, the practical limitations. Here, in case of refrigerator, coefficient of performance can be much higher than 100%. Thank you for being with me.